Welcome back. Last time we talked about empirical formulas, but before we could figure out how to figure out the empirical formula, we need to talk about the mole. So atoms are really, really tiny. We can't actually count individual atoms. There are too many. It would take all day. And we can't really work in mass, because the atoms of different elements have different masses. So we need some sort of compromise, some way to work in something we can measure, mass, and relate it to the number of atoms. That's the mole. 1 mole of any substance is the number of atoms or molecules necessary to give you a mass in grams equal to the mass and atomic mass units of the individual atom or molecule. Or, I should say, the average atom or molecule, because remember, isotopes. Now, the concept of the mole was developed by an Italian scientist named Avogadro. He was studying the behavior of gases, and he realized that the physical properties of the gases depend more on the number of particles of the gas, atoms or molecules, than it does on the mass of the gas. So, he formalized the mole as the number of particles necessary for the mass to be equal to the mass at AMU. And he found the number of particles necessary for that, and we call that Avogadro's number, capital N subscript capital A. And it's 6.022 times 10 to the 23rd particles per mole. That is a really big number, just because atoms are so very, very small. That's 6.022.0000000000000000000000000. Yeah, that's why we have exponential notation. Now, in practice, what that means is that for any substance, if you have 6.022 times 10 to the 23rd particles of that substance, you have 1 mole of that substance. And it doesn't really matter what the substance is. It could be carbonic acid, sugar, dinitrogen pentoxide. It could be pennies or puppies or anything else. If you have 6.022 times 10 to the 23rd of something, you have 1 mole of that thing. So here we have carbonic acid. 6.022 times 10 to the 23rd particles is 1 mole, is 62.02 grams of carbonic acid. Sugar. 6.022 times 10 to the 23rd molecules of sugar is 1 mole of sugar is 180.2 grams of sugar. Dinitrogen pentoxide. 6.022 times 10 to the 23rd molecules of dinitrogen pentoxide is 1 mole is 108.0 grams of dinitrogen pentoxide. So, remember, mass is a measure of the amount of matter. Moles is a measure of the amount of substance. So when I say substance, I mean molecules or atoms or ions. The individual items. That's why we have to work in moles, because it's directly related to the number of particles. But we also have to work in mass because that's something we can measure in the laboratory, because we can't count the individual particles. So we have to have the relationship between moles and mass. And I reflect that a little bit over on the other side. With different substances, same mass, different moles. So, acetic acid, HC2H3O2, 85 grams is 1.4154 moles, or 8.524 times 10 to the 23rd particles. 85 grams of water is 4.7183 moles, or 2.841 times 10 to the 24th particles, 10 to the 24th molecules. And finally, nicotine, C10H14N2. 85 grams is 0.52393 moles, or 3.155 times 10 to the 23rd molecules of nicotine. This math isn't particularly hard. You'll get used to it soon enough. But how do you do it? You're going to have to work with Avogadro's number, for one thing. 6.022 times 10 to the 23rd per mole. We don't usually write particles there, because it could be atoms, or molecules, or ions, or puppies, or formula units. Now, formula units is something we use for things that don't have molecules, ionic compounds. So, NaCl, sodium chloride, that's an example of an ionic compound. There's not really a unit of sodium chloride. Ionic compounds don't have molecules. It's a network. Okay? A whole bunch of positive ions and a whole bunch of negative ions held together because opposite charges attract. However, there's that ratio, the empirical formula, NaCl. So we call the NaCl the formula unit and use it as kind of a stand-in for a molecule. It works in the exact same way as a molecule, and it will give you all the exact same answers. So that's why we talk about formula units sometimes. So ionic compounds don't have molecules. They just have those ratios, the empirical formula. So NaCl, just a 1-to-1 ratio. Aluminum oxide, Al2O3, that 2-to-3 ratio. So instead of talking about molecules, because those don't exist for ionic compounds, we talk about formula units, the smallest possible ratio. It works in the exact same way as molecules, and you do the exact same sort of math, and they give you all the same sort of answers for work in the laboratory. Because it's functionally the same, you can think about it in all the exact same ways, but remember, for ionic compounds, there is no molecule. The other thing we have to work with, in addition to Avogadro's number, in order to work with moles, is the formula mass, or molar mass. So whether you're working with an empirical formula or a molecular formula, you're working with the formula mass, or molar mass, where Avogadro's number takes you between moles and particles, whether that's atoms or molecules or formula units. The formula mass, or molar mass, takes you between moles and mass. The formula or molar mass is fairly straightforward to find. It comes directly off the periodic table. Remember, 1 mole of something is the number of particles necessary for the mass in grams to be equal to the mass of the single particle in atomic mass units. So carbon has an atomic mass of 12.011 atomic mass units. Therefore, 1 mole of carbon atoms, 6.022 times 10 to the 23rd carbon atoms, has a mass of 12.011 grams. 1 mole of carbon dioxide is 44.01 grams of carbon dioxide. 1 mole of sodium chloride, 6.022 times 10 to the 23rd formula units of sodium chloride, is 58.44 grams of sodium chloride. All you have to do to get those numbers is add up the atomic masses of all the atoms in the chemical formula. And those come right off the periodic table. For example, here's sugar. 1 molecule of sugar has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. When you look at the periodic table, each carbon atom has an average mass of 12.011 atomic mass units. Remember, right there on the periodic table, right down at the bottom. Each hydrogen atom is 1.008 atomic mass units, and each oxygen atom is 15.999 atomic mass units. 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms, you add them all together, it's 180.156. Now, what are the units on that molar mass? Grams per mole. That is to say that every mole of sugar has a mass of 180.156 grams. Or, if you have 180.156 grams of sugar, it's the exact same thing as having 1 mole of sugar. So, you must be able to get from, the numbers on the periodic table to the formula mass, or molar mass, of any chemical formula. It's an essential thing that is going to follow you through the rest of the semester of chemistry. Get good at it now. So here I have a table with a bunch of chemical formulas on there, a bunch of chemical compounds. Go ahead and do some practice. Before we do, let's look at this compound over here on the right. That number outside the parentheses applies to everything inside the parentheses. What it's saying is that the thing inside the parentheses shows up a certain number of times. Okay? Rather than writing the same thing over and over and over again, you can just write, bing, that thing, and have it show up a certain number of times. So for that compound, there are 3 of the NO2 groups attached to that formula. So that means that there are 3 nitrogen atoms and 6 oxygen atoms. So now, go ahead, pause the video, try to find the formula mass of each of these compounds. I'll wait. And welcome back. Let's go ahead and get rid of that box. Those are the formula masses for each of those compounds. Hopefully you got the right answer. If not, well, Google it. Practice finding molar masses or finding formula masses. This is something you need to do. And let's go ahead and take a quick detour to talk about the diatomic elements. This is another thing that's going to keep showing up, and it's something that'll cause you a bit of trouble. The diatomic elements are a number of elements that always show up in pairs. That is to say, in their natural form, they're not individual atoms. They're molecules with 2 atoms in them. Di means 2, atomic, Atoms, diatomic, 2 atoms. One way to remember them, you can come up with your own mnemonic if this doesn't work for you, is Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Those are the diatomic elements, the ones that always show up in pairs. In their natural form, as elements, they're always a pair of atoms. And that's important to remember because an atom of hydrogen has a weight of 1.008 grams. But a molecule of hydrogen is 2 atoms, is going to be 2.016 grams per mole. Likewise, an atom of oxygen would be 15.999 grams per mole. But a molecule of oxygen is 2 atoms of oxygen is 31.998 grams per mole. You gotta remember these things or you're not gonna get the right answers. So remember Dr. Brinkelhoff. Otherwise, you're going to die alone in the rain, unloved, eaten by possums. Or maybe not. Maybe you'll just do poorly on the test. Whatever. Remember the diatomic elements. See you next time.